Okay, welcome to lecture 2 of dynamics. The first lecture was just a sort of a course syllabus introduction. Today we will talk about motion in a straight line. But before that, I wanted to talk briefly about what the course is about at a very high level. The course has two parts. The first part covers objects which are called particles, and the second part covers what are called rigid bodies. Particles are objects whose orientation is not really useful or important in tracking how it moves. And particles can be represented by a single point. Okay, so imagine this object, which is represented by a point moving along this curve that you would call a particle, I guess. That could be a representation of a particle. Rigid bodies usually have some finite extent and rigid meaning the shape of the object does not change. And for our purposes, they are objects whose position and orientation are important and may be important for understanding their movement. They're represented by position, in other words, where they are in space, and potentially angles that describe its orientation with respect to some reference frame. Okay, so this could be a rigid body, and maybe it's moving along this curve, but also maybe spinning, so its orientation changes. Okay, so that's two big sort of pieces of the course. Of course, generalizing rigid bodies further, you have deformable bodies, bodies that change shape, but bodies that change shape are beyond the scope of this course, and we, I suppose, various of you will be thinking about deformable bodies in a mechanics of materials course. Okay, so that's sort of a high-level view of the course. So let's move on to motion in a straight line, specifically motion in a straight line of particles. Okay, imagine we are going in a straight line. That's a straight line. This is the origin, and this black dot is a particle moving in a straight line. Okay, and we are representing the position of this particle with respect to some origin by this notation, by this symbol s, by this variable s, which is a displacement s from origin O. Okay, or it's a position of this particle on the straight line. All we're going to do is think about the relationship between position, velocity, and acceleration in today's lecture. Position. If you want to go from position to velocity to acceleration, what do? You do differentiation, right? You take position, differentiate it, ds by dt equals velocity, and then dv by dt equals acceleration, which is of course equal to d square s by dt square. In other words, the second derivative of position. If you want to go from acceleration to velocity to position, in other words, backwards, you do integration. Now let's look at how to do integration. Some of this is quite familiar to all of you and from your freshman or introductory physics classes, but some of them may be perhaps unfamiliar. Okay, so let's think about integration going from acceleration to velocity. Case one, okay? Say the acceleration is known as a function of time t, okay? And you will sort of see why I'm saying this, because we're going to talk about acceleration as a function of other things as well in a minute. But let's say acceleration is known as a function of time t. So what we have is dv by dt, which is acceleration, equals a of t, right? So this is just representing that acceleration is a function of time. Now, how do you integrate an equation like this? Notice that a is not necessarily a constant, right? Acceleration is not a constant. If it was a constant, then you could use some of the formulas that you guys learned in your introductory physics classes. But here, it's not necessarily a constant. So we will need to actually do an explicit integration. So we can do that by bringing dt up. so that we have dv equals a of t dt. Integrate on both sides like so, and we can um, place limits on the integration. V naught is the initial time. V is either the final time or the velocity, V naught is the initial velocity. V is either the final velocity or the velocity at time t, where V naught is the velocity at time t naught, okay? You can think of V naught and t naught as initial velocity and initial time. V is the velocity at time t, okay? So we have these two integrals on both sides. Integral dv is just v. We go from v naught to v, so it's v minus v naught here. The right-hand side just comes by exactly as is. So we have integral t naught to t, a of t dt, okay? And then we can rearrange this equation where we keep v on the left-hand side, bring v naught to the right-hand side. So v of t equals v naught plus integral t naught to t, a of t dt, okay? What does this equation say? It says that the velocity at time t equals the initial velocity plus the integral of the acceleration over some time period t, okay? So that's what this equation represents. Final velocity equals initial velocity plus integral of acceleration, or current velocity equals initial velocity plus integral of acceleration until the current time. If you are precise or rigorous about mathematical notation, one has to use a different t for the t inside this integral versus the t outside the integral. People conventionally use t dash inside the integral versus outside. But for the purposes of this course, we can just use the same notation inside and outside, and we'll be fine. Okay, so that's acceleration, going from acceleration to velocity, if acceleration is known as a function of time. Let's look at an example, a very simple example. Say acceleration equals 3 plus 4t, okay? So that's how it depends on time. What does this equation mean? It means that the acceleration is initially 3 meters per second square, and then increases linearly with time. So acceleration keeps increasing, okay? And you're given the initial velocity, v naught equals 3 meters per second. Initial time, t naught equal to 0. And you're asked to determine v of t, namely the velocity is a function of time. How do we solve this problem? We just use this equation, v of t equals v naught plus integral a of t, t naught to t. V naught is 3. A is 3 plus 4t. Dt is 0 to t. So just bringing this over, 3 comes over. Integral of 3 plus 4t is 3t plus 4t squared divided by 2. Apply the limits. If you plug t in here, you get the same expression. If you plug in 0 here, you just get a 0. So essentially what you have is 3 plus 3t plus 4t squared over 2, which is 2t squared. So v of t equals 3 plus 3t plus 2t squared in the same units provided, okay? And that's the answer. That's v of t. So hopefully that's relatively straightforward. So what you want to do to solve problems like this is to recall your integration rules and techniques and so on. This course will require you to do some integrations and solving some equations, but they will be relatively simple integrals, I guess. So integrals like this, where integral of t squared is t cubed over 3, integral of t is t squared over 2, etc. Okay? Okay, so that's if you wanted to integrate acceleration to get velocity, if acceleration is known as a function of time. Here we have sort of a similar situation where if you want to go from velocity to position, and velocity is known as a function of time, then again it's a straightforward integration. So if you have v of t, velocity is a function of time, equals ds divided by dt, then you can bring dt up here. You have v of t dt equals ds. Integrate both sides with respect to uh, whatever the variable is on either side. So you have s naught to s, t naught to t, v of t dt, and you can bring that here. Integral of ds is just s naught to s, which gives us s minus s naught. When we say s, we really mean s of t. In other words, s at time t equals this integral. And we can rearrange this part to say the position at time t equals the position s naught at the initial time plus the integral of the velocity time, with respect to time, from the initial time to now, t. Okay, so this is going from velocity to position, exactly analogous to going from acceleration to velocity. If you're given acceleration as a function of time or velocity as a function of time, all you have to go one step up is a simple integration. Okay, this is if things are known as functions of time. Um, things become perhaps a little bit more interesting, a little bit more subtle, if, for instance, acceleration is known as a function of velocity, v, rather than as a function of time. Okay. So what is the situation in which acceleration may be known as a function of velocity, v? Um, I'll let you guys think about it. I guess in the official live version of the class, I'll let people think about it for a while. And people basically said wind resistance, object moving through a fluid. Electromagnetism is another example. So if you have wind resistance, an object moving through wind, the faster the object moves, the more forces are applied on the object. The wind resistance force increases with the speed with which you travel. You can sort of feel this velocity dependence if you stick your hand out of a car. I don't recommend it doing this at home, so to speak. But if you stick your hand out of the car, of course, the faster the car moves, the more force you will feel due to the wind. So that's wind resistance depending on velocity. If you have an object moving through some other fluid like water, again, um, the drag, the fluid drag force will depend on the speed with which the object moves through the fluid. Electromagnetism is another situation where the velocity of objects affects the force exerted on the object. For instance, if you have a moving charge through a magnetic field, the force on the charge depends on the velocity with which it moves through the magnetic field. And in fact, this principle underlies is sort of the principle on which electric motors are based upon. And in fact, I suppose so many things in the world, machines, I guess, depend on this principle on electromagnetism. Okay, so we see that forces can depend on velocity, and therefore accelerations can depend on velocity. So imagine, for instance, that a acceleration is actually a of v. This is to represent that acceleration is a function of velocity, and this is equal to dv by dt. Still, it's the rate of change of velocity. So how do you integrate an equation like this? Okay. How do you integrate an equation like this? We can do the same thing that we did before, where you bring dt up So we have dv equals a of v dt. So dv equals a of v dt. We can integrate both sides here from v naught to v, here from t naught to t. This left-hand side will become v minus v naught, of course. But this thing, integral of a of v dt, is equal to v minus v naught. So this is a true statement. This is a true statement, but it's not a useful statement, okay? This is true but useless. Now, why is this useless or not very useful? Think about it. You can pause and think about it. The reason it's not useful is because you cannot really do this integral unless you know other stuff, unless you already know the answer, right? So a of v dt, so this is an integral with respect to time. This is some function of velocity. In a problem like this, the velocity may change with respect to time, right? It may change with respect to time, but all we know is the acceleration is a function of velocity. We don't know how velocity changes with time. So if we knew how velocity changes with time, we can sort of plug that in. We'll get a function of time here where we can integrate it with respect to time. But because we don't know what this velocity, how velocity changes, we don't have enough information to do this integral, okay? So that's what I say here. So what can we do? So it turns out there's another trick, which is the reason why we cannot do this integral is because it's got sort of mixed variables. There's v and there's t, and we don't know the relationship between the two things. But what we can do is what's called separation of variables or isolation of variables. We have a of v equals dv by dt. What you can do is bring all like variables to one side. So there's v here, so you can bring any function of v to here so that it only, so this side will only depend on v, and then you can bring the dt here, okay? So what you have is dt equals dv divided by a of v, so that's what we have here. And we can integrate both sides. This integral goes from t naught to t, and this integral goes from v naught to v. And that's it. So a is known to be some function of v, and hopefully we can do this integral. And then this side becomes integral dt, which is just t. And if you apply the limits, it becomes t minus t naught, which is what this is. So this is the final equation for a situation where you have acceleration as a function of velocity, okay? If acceleration is a function of time, we would use this equation. If acceleration was a function of velocity, we would use this equation. Any questions? Okay. If you have any questions, feel free to write me an email or post on Carmen or etc. Let's do an example. An object falling through a fluid. We already said that if you have an object moving through a fluid, it might have a fluid drag resistance that might depend on the velocity of the object. Okay. So imagine an object falling through a fluid, maybe in a vertical line, and the initial time is 0, the initial velocity is 0, so it's initially at rest, and you're told that acceleration is a function of velocity equals g, the gravitational constant, minus cv. So this is the velocity dependence. So this is gravity. So all this is saying is that gravity is pulling the particle down, and then if the downward velocity is v, there's a drag force that pulls it up, and the drag force is proportional to velocity v, and c would be something like a drag coefficient. Okay, in any case, divided by the mass or something. In any case, let's say we are given that a of v equals 10 minus 3v in some units. Let's say these are the units. This, by the way, is sometimes called linear drag because the drag force is proportional to velocity as opposed to, say, velocity square. If it's proportional to velocity square, it might be called quadratic drag. And objects moving at a high speed actually have more like quadratic drag. In any case, this is the equation that's given, and we have to solve for v of t. Determine v of t as the problem statement. So we basically follow this principle. A of v equals dv by dt. You bring a of v here, dt up here. Integral dt equals integral dv by a of v with appropriate limits. Let's plug in these numbers. T minus t naught equals integral dv divided by 10 minus 3v, which is a of v. So this is an integral, I suppose you might remember. If you have integral dv divided by v or dx by x, the integral of that is log x. Okay, integral of 1 over x is log x, or integral of 1 over v is log v. If you have integral dv by 10 minus 3v or a plus bv, then what you have is whatever this is goes up inside the log, and then whatever the coefficient of the variable comes in the denominator. Okay, so you can look that up. You'll probably see this integral rule written up as dv integral dx divided by a plus bx equals log of a equals a plus bx divided by b or something. Okay. In any case, we've done the integral. We can plug in t not equal to 0, v not equal to 0. So this becomes t minus 0. This becomes log of 10 minus 3v divided by minus 3 minus, then we plug in v not equal to 0, which gives us log 10 divided by minus 3. You can bring the minus 3 up here, so we have minus 3t here. And here we have log 10 minus 3v minus log 10. Log of a minus log of b is log of a divided by b. So that's what we are using here, log of 10 minus 3v divided by 10. Okay, 10 minus 3v divided by 10, because log of a minus log of b is log of a divided by b. Now, if we want to find, so here what we have is time as a function of velocity in some sense, right? We really want velocity as a function of time rather than time in terms of velocity. So how do you get velocity in terms of time? We need to somehow get rid of the log, and you do that by exponentiating both sides. Okay, getting rid of log is done by operating this function by the inverse of log. Inverse of log is the exponentiation operator. So do e power both sides. So this becomes e power minus t, 3t. This becomes e power log whatever. And e power log whatever is actually whatever. So the e and the log gets cancelled essentially because they're inverses of each other. And whatever is here comes out here. So that's what we get. E power minus 3t equals 10 minus 3v divided by 10. And we can rearrange things, bring the 10 up here. 10 e power minus 3t equals 10 minus 3v. Bring the 3v here, 10 e power minus 3t here. You have this. Bring the 3 down, and then you get this expression. Okay. So this is the final expression, which is v of t equals 10 minus e power minus 3t divided by 3. Okay. So this is the velocity of the particle falling down as a function of time. You can try to plot what this function looks like if you're curious. How does the velocity change as a function of time? So if you plug in t equal to 0, the initial time, then e power minus 3t becomes e power 0 E power 0 is 1. Um, so you get 10 minus 10. So you get v equals 0 at t equal to 0, which makes sense because that's sort of what we used already in the integration. And then as time t goes to infinity, or t becomes very, very large, then e power minus infinity, or minus a large number, is basically very close to 0. So as time grows, this term becomes 0, and what you're left with is 10 over 3. Okay, so the function v of t, where t is actually in the x-axis, um, becomes like this. It's sort of 0 and then slowly increases until it approaches this velocity 10 over 3 as time t goes to infinity. And this sort of steady state velocity is sometimes called terminal velocity. Okay, this is a term that you may have heard about. In any case, this is the answer that we sought. We're not really requiring you to plot this. We didn't ask you to do that. I'm just saying that this is what it will look like, this curve. But in any case, this is the answer. Any questions, I guess? If you have any questions, send me an email. Okay, so the final thing is case 4, I suppose, or possibly, I suppose, let's say case 4. What if the acceleration is known only as a function of position? Okay, so here acceleration was a function of velocity. You might also have situations where acceleration is a function of position. Okay. Examples are, I'll let you guys think about it. I guess I let people think about it in class, and various students said gravity, right? So gravity, not when we are very close to Earth, when it's essentially looks like a constant mg, but when substantial distances are involved, the gravitational force depends on how far you are from the Earth, or how far two objects are from each other, right? This is sometimes called Newtonian gravity, or the inverse squared law of gravity. Other examples are electrostatics, where you have two charges. Again, the force between them depends via an inverse squared law. In other words, the force is proportional to 1 over distance squared. Springs, again, the force applied through a spring depends on the positions of the various objects. For instance, the spring force depends on the stretch of the spring, so it depends on the position of the two endpoints of the spring. Similarly, if you have two magnets, the force between them depends on how close they are or how far away they are. So these are all sort of standard examples that, like I said, various students suggested during class. I wanted to mention that there are lots of other examples, especially in the modern engineering context. A lot of machines, robots, machines could involve rockets, whatever, airplanes. All of them involve feedback control. There are sensors on these machines, and then there are actuators. Actuators meaning motors, other things that can apply forces. And usually these machines do what's called feedback control, which is use sensor information about the position of the object, the velocity of various parts of the object, and then apply forces on the object or the robot that depend on the position or depend on the velocity of the various parts of the machine. Okay. For instance, this is more velocity dependence rather than position dependence. Cruise control. Imagine cruise control on a car. That's really about applying forces, like increasing the acceleration, for instance, as a function of the car's speed. If it's too slow, apply more force. If it's going too fast, apply a decelerating force. Okay, so that's cruise control, where you're applying forces that depend on the car's velocity. If you're trying to land a rocket, like a SpaceX rocket, for instance, and while at the same time trying to keep it vertical, that's a situation where you might want to apply forces on the rocket to keep it vertical. So that depends on the position of the various points, namely the angle of the rocket, and potentially you apply forces that depend on how far the rocket is from the ground. The rocket ship, I guess, the vehicle is from the ground, and potentially also it depends on the speeds at which the object moves. Okay, and you can imagine a million other robot situations. I guess I think about walking robots and people, and again, a lot of the control depends on position and velocity of the various parts of the body of the robot. Okay. In any case, that's motivation for how forces, or in this case, accelerations, may be known as a function of position. Okay, control. So if we have such a situation where you have a of s, right? S meaning position, acceleration is a function of position, um, equals, of course, still dv by dt. Um, so this is a bit more complicated than the previous example, it turns out, because if we had only two variables, previously we had two variables in this equation, v and t. So acceleration is a function of v, so this part is just a function of v. Here we have v, here we have t. There's only two variables, and we could separate the two variables, one to each side. T comes here, all the v terms come here. Okay. Here, on the other hand, there are three variables. There is position. So this whatever this is will depend on position. Here we have velocity. Here we have time. So there are three variables. So we cannot really do this isolation business. We can, because there are only two sides and there are three variables, we can't really bring everything of one type to one side and everything of another type to another side. So what we need to do is sort of convert these three variables into two sort of variables, so we can actually isolate them to each side. So this is a trick, I guess, someone invented, I want to say about 300 years ago, close to the beginnings of calculus, late 1600s, I suppose, where you say a of s equals dv by dt, of course, but dv by dt can be written as dv by ds, ds by dt. So you can imagine canceling these things to get dv by dt. This is basically using chain rule of differentiation, which hopefully all of you have learned. So dv by dt can be written like this, and then ds by dt itself is just v. So you're converting dv by dt equals dv by ds and v. So now, if you sort of forget this for a moment, you have a of s, which is a function of s, and then you have v, and then you have s. What we've done is basically removed the time, dt, from this equation. So once you have this, you can separate all the v terms, separate all the s terms, which is what we do here. So it's a of s ds equals v dv, and we can integrate both sides, like so. Integral a of s ds equals integral v dv. Integral v dv is just v squared over 2. We can apply the limits. You get v squared minus v naught squared divided by 2, and that's it, right? So this is all we can do so far. We can rearrange things a little bit if we want, but we cannot do too much simplification unless we actually do this integral, which will depend on the specific function, acceleration, as function of time, as function of position, that may be given in the particular problem. Okay, so that's the final answer. If you do this integration, what we will get is some expression that is a function of position here. Here we have velocity. We can rearrange this to get velocity as a function of position. But what if we want velocity as a function of time, right? So at the end of this, we'll have velocity as a function of position. So if you have velocity as a function of position, we can integrate that again to get velocity as a function of time, or position as a function of time. Okay, so how do you do that? It's exactly the same as before. We have velocity as a function of position. So we have v of s, like so, which is ds by dt. Again, we have two variables, s and t. This is just a function of s, so it's just s here, s stuff here. And then we can bring the s terms here, dt up here. So if you have velocity as a function of position, this is the equation that you get, okay? We have ds by v of s equals integral dt, which is t minus t naught. So we have integral s naught to s, ds by v of s equals t minus t naught. And if we do know the velocity as a function of position, for instance, from this kind of procedure, then we can plug that in here, integrate, and then solve for position as a function of time, okay? And then if you want velocity as a function of time, you can differentiate it further to get velocity as a function of time. So those are the sort of various possibilities for motion in a straight line. So all these things correspond to motion still in a straight line. What have we done? We've talked about going from position to velocity to acceleration using differentiation, and then going from acceleration to velocity to position using integration. This differentiation, integration, and the integration depends on what it is, whatever you're integrating, what it is a function of, right? If you're integrating acceleration, it could be a function of time, velocity, or position, and depending on what it is a function of, the procedure is different, okay? Sort of at the end of all this, you might ask, hey, what if the acceleration, for instance, is a function of both position and velocity, and maybe even time? How do you solve a problem that has that flavor? It turns out that in some simple situations, you can still solve such problems using sort of analytical techniques. But if you have more complicated dependence on positions or velocity or time, it turns out that there is no simple analytical formula like these, but you just have to use a computer. Even for motion in a one dimension, you're just essentially stuck solving the equations using numerical integration, basically using a computer to do the integral. Okay, so let's stop there. I suppose in the recitation sections, you will see examples, further examples of doing these kinds of integrations.